welcome to Introduction to Prescription Part 2, or Prescribing Part 2. And today we'll be covering shell materials and shell modifications. So today we'll be talking about the shell materials, which is on our portal. From that perspective, we've covered that last time, logging in and so forth. So shell materials, and here at Footwork, we use three types of shell materials. Predominantly, we print from 3D print nylon PA11. We also use EVA, and that is now being machined as well, up until about around Christmas time, or before Christmas, probably about nearly 12 months ago now, come to think of it. We were still vacuum pressing EVA. We are no longer vacuum pressing with EVA. Problem with vacuum pressing EVA, it's very, very labor intensive. You literally have to machine out the positive block of the design, then vacuum press the layers of EVA on top of it, and then grind all that off. Where literally it will take you, a good part of an hour to grind a full length EVA device. And then you're looking at consistency and reliability. How much do you grind off? How thick do you want it? And we always had issues with 4-foot being too thick or too thin, and so forth. And look, it's not a nice job to do. And now we've got our software humming where we can actually design the EVA and machine it. So we can actually select the thickness of the 4-foot that you want. Our standard 4-foot thickness is 3 millimeters in a full length EVA, 2 millimeters in a web length EVA, but you can select it to be whatever you want. Some podiatrists will even specify, 5 mil or 6 millimeters if they want sweet spots, etc., to be placed in there. So the other material, as I mentioned, is nylon PA11, which is a natural product. It's like plastic. It behaves very similar to plastic. There are some differences within it, and we'll go over that as well. And then there's carbon fiber. The main carbon fiber that we use is Superform, which is a combination of carbon fiber and polypropylene. It molds very well. However, look, we use very little of it. We'd be lucky to do 1 or 2 pairs a week. So it's very seldomly used. We just find that, again, we can get so much more with different thicknesses and thinning out different parts of the shell through the nylon PA11. It is much more easier to use. And again, we have to vacuum press that material. So it goes down to how much do we vacuum press, make sure it's heated up enough, make sure that it contours the positive cast, for a better word, which is an MDF block, and it contours that. And again, there's a lot more art form involved, and we are depending on the technician to almost do the job of a podiatrist. Whereas with the EVA and the 3D printed material, as a design, our podiatrists who are designers in the lab design and pretty much are responsible for 99.9% of the finish of the product. Of the shell itself. So that's what we are trying to get to give the prescribing podiatrist the consistency and reliability of our design, to make sure it's always is the same. So that, if you want to repress or a remake, see, I'm still using old words, repress. If you want to remake, we want to make sure that it is consistent. It is exactly the same as you've had before, or with whatever changes you have requested. So the device does not come back different. And moving to a platform where everything is done in design allows us to do that. Okay, so reliability, consistency, repeatability. I can never get that word out, but I mentioned it today. So carbon fiber Superform. We also use carbon fiber TL2100, which is a carbon fiber with acrylic compound. That material looks like it's a much shinier carbon fiber. It looks like the stuff you see on car dashboards. What we find is that it tends to be a lot more brittle, and those devices tend to fracture. We used to make our cycling orthotics out of it. We no longer make our cycling orthotics out of it. We now 3D print our cycling orthotics. We have adjusted or changed the shape slightly, updated, and we are getting great results from the feedback that we're getting from all the professionals that we have fitted out over the last 6 to 9 months with the 3D printed orthotics as opposed to the carbon fiber ones. And again, cycling orthotics is something that we do specifically here. It's a specific design, and we do run workshops. Although now with COVID-19, we are starting to be a little bit more hesitant about having people inside. But the cycling orthotic is something that you've got to do as a hands-on workshop. It's probably not something we'll be able to do as on a Zoom webinar. Maybe more like a multi-camera where we'll have some subjects and do a virtual assessment and so forth. So it's something we'll definitely look at down the track if we cannot have people inside and run hands-on workshops. But that's a story for another day. Okay, so we're going to shell materials again. So we'll go carbon fiber, we have semi-rigid and semi-flex. Then with EVA, we have soft, medium, and hard. Soft being around a sort of 180 geometer, medium being about 280, and hard being around the sort of 380 to 400. All our EVA at this stage comes in a black color. So soft, medium, and hard, all our EVA devices come in black. We don't as yet do dual density, which we used to do with the vacuum press devices, but it's definitely something that we are experimenting with and how we can utilize it. So keep your powder dry when you're ordering for dual density devices. At this stage, it's something we're not offering, but it's something that we'll definitely do in the future. We'll also go through some design things with the EVA devices and how you order a full length design orthotic. We can actually use templates that you supply us, etc. So it's quite easy to match the full length EVA device perfectly to the template of the patient's shoe. And with the EVA device, you can select a 3/4 length, which is your standard length device. You can select a web length. You can also select a full length device. Then moving on to our 3D printed nylon PA11. One of the questions we get from podiatrists is how does it compare to polypropylene, what we used to machine, in stiffnesses and so forth. So I'm going to highlight 3 millimeters for a reason here, because what we found is that 3 millimeters tends to be pretty much spot on, the same as the polypropylene. Then as we go down in the thickness of the material, it does come down in stiffness quite rapidly. As we go down to 2.5 mil, it does become more flexible. So 2.5 mil is probably closer to 2 mil polyprop, and 2 mil is even thinner than more like 1.5 mil polyprop. So there is a big jump. There is ways that we can overcome that by utilizing brace bars without having to thick or make the whole shell thicker. We can actually make supportive bars and structures. So it does behave more like a 2.5 mil. And it's much more easier to modify if you ever need to modify it. And again, it's one of the things that we'll talk about with our modifications. Moving forward from that, however, it's in the near future, once we've updated our portal, there will be the option for you as a podiatrist to actually request increments of 0.1 of a millimeter. So if you've been used to sort of saying 2.5 is too flexible, 3 mil is too stiff for you, you'll be able to order 2.6, 2.7, 2.8, and that's coming up in the next few weeks. So 3 millimeters is the sweet spot. As I said, 3.5. As we go to a thicker material, it does ramp up quicker again. So 3.5 is closer to 4. Then 4 is more like 5, and 4.5 is closer to 6, and 5 mil is 6 plus. So you're talking 7 millimeters. 5 mil can be quite rigid. Now, just like polypropylene, the device is also, the stiffness of the device is also reliant upon the design of the device. So the more archier the orthotic is, the more stiffer the device will be because the material locks up. And that goes the same for whether you're talking about polypropylene, nylon PA11 or PA12, which we don't use, but also carbon fiber behaves very similar. If you add any other modifications to it, such as plantar fascial accommodation, it will stiffen the material up because we are creating or adding curvatures to it, which will lock the material up. So in the same as the previous materials, polypropylene and carbon fiber, the nylon PA11 behaves very similar. So let's have a look at some of the designs that we did. We'll go back to our EVA. And before we go into modifications, we might just actually chat about what I've done here is prepared a design. So what we have is a design of an orthotic, and we've selected a podiatrist that has actually sent us a template, not a very nice cut out one. So cut and paste for that one's probably failed in primary school. A podiatrist that has sent us a template. What we would like you to do, you don't have to send the template itself. You can actually take a photo of the insole of the shoe. You can take a photo of the insole of the shoe. You can take a tracing on paper of the insole of the shoe and simply give us the length measurement from bottom of the heel to the end of the toes. Because if you take a photo, it doesn't often scale up when you upload it, it gets shrunk. But we have the measurement, we can then scale the actual insole up. So if you have a look at this, the one on the screen, we can actually increase or decrease it. So if you told me that that was 270 mil, we can actually scale that up to 270 mil in length, and exponentially it will increase to the right size. So let's say this one we had at that size, we simply bring it in up against the material, the design of the orthotic itself, and then we can adjust the design to match the length and parameters of the actual insole. So even talking about if it needs to be a little bit wider, we can expand that a little bit as well, make it wider, and we can match that insole pretty much to a T. So when I now move that away, I might have to just adjust that a little bit, and that there. And when I create our mesh for our EVA device, we can match that device length and shape to any template that you supply us with. So that pretty much goes for full-length EVA devices, or even if you want to send us one for a web-length device, a template, we can match that perfectly. So that's one of the benefits of our new software. Secondly, one of the other things that we can do, and I might just actually get rid of that. So we take it out of the back. One of the other things that you can do is have everything done intrinsically. So again, we'll talk about a lot of the modifications that we do, but a lot of the padding that we do, you know, your Mority pad and things like that, we can actually inbuild in the design itself, which if we get enough time, I might do it. But having to think about that's a little bit more time, and in an hour, we might not have enough time to do it. So that will be another workshop on its own, but hopefully you get the picture. So now let's go back, custom orthotics. Have we got any questions, Baz, about EVA device? Anyone got any questions about full-length EVA devices?
Excuse me. Yeah, we have a couple. The first one is, what's the difference between carbon fiber and PA11 in terms of weight?
In terms of weight, look, carbon fiber, you can get carbon fiber stiffer. So one of the products that we do is called the Joanne, named after Joanne Michelitzis, who's done a lot of research on toe walking in kids. And there's a product called Joanne, which is a full-length carbon fiber orthotic out of ultra rigid, which is not actually on our prescription form. You have to specify Joanne to get the ultra rigid for an ultra rigid for kids for toe walking. So the carbon fiber that we have for that purpose is much stiffer. To get the same stiffness out of 3D printed, you know, we'd have to go to about 4 or 5 mil, whereas the carbon fiber, I think from memory, is about 2.5 or 2.7 mil thick. And it's a very, very rigid device, which is used to treat with kids with toe walking, along with the program they have at Monash Medical Centre and some of the health centres they're associated with. They do a lot of work with physios and surgeons and so forth as well. So it's not just sticking a full-length orthotic in the shoe. Again, that is something that we're going to cover in one of our other workshops. So carbon fiber is much stiffer, but that's probably one benefit of the carbon fiber. But if you don't need an ultra rigid device, and you know we no longer produce our average orthotic these days is between 2.5 and 3 mil 3D printed. That's our average thickness. So we're not seeing many devices going, you know, for 4 or 5 mil thickness. So carbon fiber will do that. The other thing I probably should stress is that the carbon fiber, the way that we do it, is actually more expensive. We have a surcharge on carbon fiber because it is a lot more expensive as a material, plus the extra labor involved. That's something that's reflected in our price list. I think the carbon fiber is a surcharge of $25 or $30 off the top of my head. Please don't take my word for it. So I hope that answers the question. What else was it, Baz?
Can EVA be 3D printed?
Good question. EVA, no. There is a material coming. The rep was supposed to come and see me and show me an example this week, and he hasn't shown up as yet. There is a material coming out called TPU. It's, again, technology developed by Hewlett-Packard, which is the same technology that we're using for 3D printing for our devices. And It is coming. So TPU is a rubber-like material. Look how fast we'll be able to print it compared to what we're printing now and compared to what we're doing now. But it is definitely coming. Not yet, but give it a year, maybe two, and it's something that we'll definitely have access to. Yep, that's it.
We have four more.
Okay, go.
So when measuring the insole of a shoe,
Yep.
the dorsal or the plantar aspect?
The longest part. So the longest part. So it would be, in most of the time, it will be the dorsal, and we will measure the longest part of our insole as well. Easiest way to remember is just the longest part of the insole, which most of the time, taking a slight heel cup into account, you do the dorsal.
The next one is when ordering EVA, are there weight limits for soft, medium, and hard? In other words, 120 kilos. Do they bottom out soft options too quickly?
They will, but it's also what you want to use it for. There are people who are 120 kilos who are diabetics who wouldn't tolerate a medium or a hard with lesions and so forth. So it's not just the weight of the patient, but it's also the function that you want to be able to have with that. Okay, so soft, medium, hard, it's more of a functional. So personally, if I'm looking for a functional orthotic, I would not be looking for an EVA device. The problem, again, if you can see that, problem with an EVA device is that in order to give you support, it has to be filled in all the way through. If a shoe has some sort of contour through it, the EVA device will change shape inside the shoe. So if you want to exert exact pressure or force to a foot in a particular spot with an EVA device, you'll be able to do it much less precisely than you will with a 3D printed device. So EVA devices are, from my perspective, purely accommodative. There are podiatrists that order, Blake inverted type orthotics out of EVA, but again, they do look quite chunky because all that support that we've inverted all through the arch has to be solid filled in, because otherwise it just collapses. So EVA devices are more bulkier. Make sure you have the shoes to accommodate them, and don't expect for them to function the same as a 3D printed device. Okay, is that it?
Next question is, are you able to choose a thickness in a full-length EVA device?
100%. You can select. So our standard is 3 millimeters, but if you want that to be 5, 6, 7, 2, you can do that. We probably don't go less than 2 because it gets too flexible and so forth. And by the same amount, you can actually select a heel raise. So the heel raise will be built in. If you select the heel raise, the device will simply be raised at the heel and will be down to 3 millimeters at the forefoot and continuing on. But you can actually select it. So if you want a 10 mil raise at the heel, 6 mil in the forefoot, down to 3 mil at the toes, we can do all that as well quite easily. Okay.
Now, the last one is, for the EVA devices, are you able to inbuild pour-on into the device? In other words, pour-on buttons?
100%. So what I'll do is I will show you now. So there's my orthotic. If, for example, you wanted to offload, you can see I've got a, not sure if you can see it, but I've got a bit of a spot that's touching around here, okay? So let's say that might be a lesion, okay? So if I want to, oh, you can see it better in this picture. So where that's touching, if I want to do a spot test, groove modification, 0.2, subtract. If I want to do a sweet spot around that area and then offload it, transparency, if you can see that, I've now offloaded it. If I want to do it even more so, I can do that, and then we can fill it with pour-on or whatever material you want, whether it be Plastazote and so forth. And by the same token, easiest way, if you have a sweet spot that you want to offload, and we'll talk about sweet spots later on, is simply stick a button or something on a scan, a button of felt that you can see as an offload, but we'll cover the sweet spot. So yes, we can do that and do it quite easily. That's it?
Yeah.
Great. Okay, fantastic. So now we'll move, we'll have a look at the modifications. So we'll go through medial heel skive, lateral heel skive, triplanar heel skive, intrinsic medbone cuboid notch, and all the other modifications. So I'll refer to this page, go back to it every now and then. I'll try not to all the time because it does create a little bit of a delay for me. So if I go back to my design And there we go, you've got design, open recent. We'll go through to that. So there's a design. Actually, I had one prepared earlier with a skive. So we'll talk about skives for now. So let's talk about medial heel skive. So if I add and do a skive, so medial heel skive is added at 15 degrees to the correction that we've actually set the reef foot at. So this reef foot is set at 0 degrees. So there's my medial heel skive at 15 degrees. And if I want to make it slightly larger, so I can increase that in size, so it'd be a large. What we had was a medium. If you want to make it smaller, you can make it smaller as well. So that's a medial heel skive. If you want a lateral heel skive, we literally do the same thing. And we do that, as you can see, on a lateral heel skive. So there's a lateral heel skive we can do as well. So medial heel skive, lateral heel skive. Why would you use your medial heel skive? Medial heel skive is a way of adding reef foot correction to a device if you don't want to affect the shape of the arch. So you want an as is or a mid, but you want a bit more reef foot correction without actually changing the shape of the arch. You can use a medial heel skive. And a medial heel skive is done purely in the frontal plane, so 15 degrees on the medial third of the calcaneus, purely in the frontal plane. And it does bulk the device a little bit, so it does lift the heel on the medial side because that's the only way that we can do it. Another way of doing a medial heel skive, when we talked about different arch fill techniques last week, was to do an as is at 0 and just put the correction into the reef foot. So what you get there is the shape of the heel cup much more without generating a flat spot. So a lateral heel skive you would use, for example, with somebody who's got cable varus foot, lateral ankle sprains. So in the past, podiatrists used to order everted devices. So now, and the problem with an everted device is that as we evert the orthotic, we drop the arch height and reduce the calc inclination angle. So if you want to conserve the calc inclination angle and the arch height, you do a device at 0 degrees, match the arch shape. And then if you want to add a lateral heel skive, you can do that. And lateral heel skive and wedge it more laterally through a plantar fifth raglan, which we'll talk about shortly. You can then also utilize higher and longer lateral heel cup as well, which was covered in the heel cup section on the previous video. So medial heel skive and lateral heel skive, purely frontal plane correction, purely inversion. Now let's have a chat about, show you how a triplanar heel skive, we move the medial heel skive a little bit more distally and give it a little bit more inversion, and it's a little bit of marking around with it. And by doing that, we move the pressure point more distally along the arch, and thus creating a little bit more calc inclination, gives you a little bit more triplanar support rather than medial heel skive. So it does give you a little bit more of that calc inclination angle support. Now with this device, it doesn't come out very well because it's a fairly flat device. As you can see, the heel here is sitting quite flat. It does not have a high calc inclination angle. So that device, we can't actually push it up as much as we would with a higher arch device. So a triplanar heel skive works really well with a higher arch device where the calc inclination angle is much higher. And we can support that by flattening that area out a little bit more, thus gaining that more calc inclination angle support. The reason why we would use it with a really flat foot or where the scan or the foot itself is very flat is because the foot doesn't move that way. So if you've got a patient with a low calc inclination angle to begin with, we can't support it with that patient. You need more frontal plane control. So medial heel skive or inversion will work much better. We do get the odd podiatrist every now and then requesting a triplanar heel skive on an inverted device. Now, there's definitely a no-no because there is no calc inclination support in that material. Again, so that's your triplanar heel skive. I'll just refer myself to what I was looking at next. Next one, we've got a intrinsic med dome and a cuboid notch. So there's my med dome, and I can adjust the shape of it to whatever I like. And small, medium, large. Now the intrinsic med dome is slightly smaller than, or slightly lower than the standard med dome because it is obviously more, it's harder, it's more solid, so we can't have the same thickness. but on average, it's around 3 millimeters thick for the average device. Now, this is quite a small device, 149 mil high, 149 mil long. So that's slightly below, it's probably about 2.5 mil thick in this case. But as you can see it, now if we want to move that slightly more laterally, because you've got a Morton's neuroma in the web space between 4th and 5th, we can move that. Again, just let us know where you want it, but the standard one will be behind med heads 2, 3, and 4, thus allowing plantar flexion of the first ray. Again, why would you use intrinsic med dome? Number one, it doesn't wear out. It doesn't give you any problems with it not being in the incorrect spot, because it is done in the design. And where the pads go and how we do our pads will be covered in our padding section in the next video. We are looking at a way of actually thinning out the material underneath the med dome, which will give us that med dome ability to produce that med dome to be slightly more flexible than the rest of the shell. It's something that we are testing at the moment. Before we release it, we just want to make sure that, you know, how much we can push it before the shells start fracturing. Because last thing we want to do is give you an option, and then you come back to us, you know, 3 weeks or 3 months later with a fractured shell because it cracked in that spot. So it's something that we need a little bit more time with, and when it's available, we'll definitely let you know. So there's your intrinsic med dome. The next one on my list was a cuboid notch. So if we have a look at, so a cuboid notch jumps in at the calcuboid joint. Again, we can make that slightly bigger. Why do we use a cuboid notch? Well, again, it's something, if you've been to one of my workshops previously or hear me speak about this, it's something that, you know, a lot of podiatrists do order a cuboid notch for our orthotics, throughout the orthotics that they prescribe. However, we don't really know, there aren't any studies or any literature that shows what a cuboid notch does. So anecdotally, what we find is that it puts pressure on the lateral part of the foot. Clearly, it allows for the locking mechanism of the calcuboid joint, which then starts in the generation mechanism of the windlass, in the generation process of the windlass mechanism. It's a modification that I would say majority of the orthotics we manufacture do have. Does it irritate? Well, look, if you've got somebody that's got an arthritic calcuboid joint, I probably wouldn't use it, but, you know, hypermobile or mobile 5th ray, and you want to lock up the lateral column, it's definitely something that I'd be using all the time. Also, one of the theories is that cuboid notch will actually aid in the plantar flexion of the first ray. So your peroneus longus, which runs under the calcuboid joint, it also attaches to the base of the first. If you press on your patient, you can quite often, in a lot of cases, see where by pressing in that area, you can actually facilitate the plantar flexion of the first ray. So if you want to do that, a cuboid notch is a good modification to use as well. One of the only time you probably can't use a cuboid notch with a design, from a design perspective, is a cord hook, because it's all cut away. Having said that, it doesn't stop podiatrists from asking for it. So cuboid notch, moving along is more lateral, is a plantar 5th ray grind. So to show you what a plantar 5th ray grind, we'll go back into our curves and go into transparency and show you our cast. So with a plantar 5th ray grind, what we do is we increase the height of the lateral column. Normally, as you can see from that image, if I change the transparency a little bit more, if you can see it, that line here is actually cutting into the foot. So we've actually put some pressure laterally. So by moving that down, we are getting rid of plantar 5th ray grind. So by adding plantar 5th ray grind, we are literally pushing up the lateral part of the shell into the foot. And as you can see from that angle, it does create a pronatory force as well. So it aids in the pronation of the mid-tarsal joint. Again, generating the windlass mechanism. It prevents the foot from sliding off the device. So if you've got a hypermobile lateral column or a metaductus, a plantar 5th ray grind is a really good way of using it. So you can actually see how much we've cut, or we've added that pressure into the lateral part of the foot. So there's my plantar 5th ray grind, as opposed to a lateral plantar grind, which is another one of the modifications that is on our prescription form. And a lateral plantar grind, we actually thin out the lateral part part of the orthotic itself. Now, the way that we used to do a lateral plantar grind when we were doing polypropylene devices is we would actually just literally grind the lateral column out to make the device thinner. Now, podiatrists would use a lateral plantar grind for two reasons. Number one is to add more flexibility to the device. So when you're making that lateral column more flexible, please remember that. So a lateral plantar grind will add more flexibility to the device, make it thinner. The way that we do a lateral plantar grind these days is we literally do a little grind. As you can see, I'll flatten that area out and thin it out by a millimeter. And that creates a thinner part of the shell, but also that's a lateral plantar grind. That's a lateral plantar grind and a plantar fifth ray grind. Plantar fascial accommodation, first ray accommodation, and cuboid notch next on my list. So let's go into plantar fascial accommodation. So plantar fascial accommodation is one of those modifications that if you add it to a prescription and the patient doesn't need it, you probably won't notice. But if you don't add it and the patient needs it, then it can be problematic. So again, one way to test whether a patient requires plantar fascial accommodation is simply dorsiflex the patient's first MTPJ, and if the plantar fascia pops out through the arch, you will need it because otherwise you'll get some irritation through the arch of the shell. So we have a little tool that we add there, and then we press create. There's my standard plantar fascial accommodation, okay? So if I wanted to make that a little bit wider, so you can see now it's a much deeper, larger plantar fascial accommodation. So again, by selecting small, medium, large, you'll be able to control it. The deeper the plantar fascial accommodation, the more curvature we are adding to the shell, the more stiff, the more stiffening effect it will have on the shell as well. So there's your plantar fascial accommodation. And look, if you want to mark your plantar fascia, you can simply put some dots on the foot when you're scanning it, whether it's through felt, or you can take a photo and then just mark the photo and upload it as well. And we can refer back to the photo if it's something specific, but the way we do it here at Footwork, we start off at the medial bisection, medial third of the calcaneus, distal part of the calcaneus, and go to the first MTPJ is where we add the plantar fascial accommodation. But if we need to move that, we can definitely move it around and have a lot more control on it if we need to. So there's your plantar fascial accommodation. I'll start it again so it moves up a little bit more and I don't get muddled up with all the different modification. So the next one on our list is a first ray accommodation. So a first ray accommodation is something we've been doing here at Footwork for the last 25 years plus when we started. With a first ray accommodation, we want to move this line away from the first metatarsal for it to be able to plantar flex. So let's do our first ray cutout first because it's something that most people see a lot more of. So with a first ray cutout, again, we use a little tool and we use our Aperture tool to actually do a first ray cutout. I'll place it there. So there's our small first ray cutout. If you want a large one, we will go down pretty much to the base of the first metatarsal. So let's say we do a large first ray cutout. Actually, I'll show you a small one first. So we'll do a small first ray cutout first. So our standard one, sorry, that's our standard medium first ray cutout, the way we do it at Footwork. So with a first ray cutout, we allow the first ray to drop under the first metatarsal. We have the ability to actually bevel that off. So, you know, all our tools we can bevel off, and so we don't have to grind it. Again, everything is done in the design process. But from that, you can see that, you know, that first ray cutout doesn't really allow the first metatarsal to plantar flex, does it? The first metatarsal starts here at the medial cuneiform, first metatarsal joint. So this area here doesn't really allow the first metatarsal to drop. It exposes the first MCPJ a little bit, but more importantly, what it does is makes the orthotic pronate, because that medial column here is no longer supported. And once you put any weight on it, that orthotic will simply pronate and drop to the ground. So you are losing with a first ray cutout a lot of the control, and you're not really getting the true function of a first tray cutout unless we do something like this, where we actually do the cutout much longer, something like this, cut it back all the way to the base of the first, where the whole first can drop down, fantastic, but we are still faced with the problem of no medial support for the orthotic itself. So the orthotic will, as you get more pressure from the foot medially through the arch, that orthotic will actually collapse. So how do we do that? How do we achieve the function of the first tray for it to be able to plantar flex without the orthotic collapsing underneath it or planating underneath it? So the way we do it here at Footwork, we add a first tray accommodation. So all we simply do is bring back and it's something that we used to do initially with plaster, and we'd actually add extra plaster to the post, to the 4-foot post itself. So we brought that back, so make it look like a first tray cutout, look in the medial view, and then we drop that away lower. So now if I show you, might be able to see it a little bit better. And if I show you the wall, we've now dropped that surface all the way away from the first metatarsal, the whole first metatarsal. But the orthotic shell is still balanced on the medial side. So we've got a nice gap here for the first tray to be able to plantar flex, and the orthotic is very functional, it's supportive. So having seen that, in my opinion, you should probably never ask for a first tray cutout. So a first tray accommodation, in my opinion, is a far, far better option for it. The only time I would use a first tray cutout is probably, as a second thought, if a patient comes to me with a pair of orthotics they've already got and we need to modify them because they're jamming up the first MCPJ function. So therefore, I would do a first tray cutout just on the old orthotics to be able to free it up a little bit, maybe heat it up and push that medial corner down to be able to balance it up. But from a start new orthotic, a first tray accommodation would be something that I would go for every day of the week and twice on Sunday, as opposed to a first tray cutout. So let me just quickly check what our next one is. Extra heel expansion, medial flare and medial wrap are the next ones on my list. So extra heel expansion, initially we give you 4 millimeters of heel expansion. So as you can see, we've got 4 mil of heel expansion there. The software actually measures that for us, and it's something that we'd already covered in the previous section on design. So extra heel expansion, the operative word is extra, and here we are told it's 58 millimeters. So if you want extra 2 mil heel expansion, we will literally pull that out to 60 millimeters. So now top right hand corner. So now my diameter is 60, and I'll just balance out the lateral shell a little bit more to match it, so it looks a little bit more balanced and the same. And there's my extra 2 millimeters of heel expansion. One of the other things to have total control over is that line in the heel cup, and hopefully you can see it through here, where we actually have the control and not having to make that lateral heel cup so steep so it doesn't cut in, and give it a little bit of an angle, which is a standard thing that we do here at Footwork. So therefore it flares away from the foot and it gives you less irritation. Now, when would you ask for extra lateral heel expansion? There's probably one main reason, and the way that easiest way to look at it is that if we can't see it here at Footwork, then you need to ask for extra heel expansion. So the main reason being, when you've got a really flashy foot, is one way of explaining it, and you've taken a non-weight bearing scan and you know that the foot will actually expand more than the average 4 millimeters on weight bearing. And you can usually get a feel for that while you're doing a biomechanical examination, because you're handling the foot, testing range of movement, subtalar, metatarsal joint, etc. And you can feel how flashy it is, but you can also see it when the patient is non-weight bearing and weight bearing. So you'll need to ask for that. So the technical term I tend to use when the foot goes splat is something that we cannot see here at Footwork. So you have to allow for extra heel expansion. Another reason why you would need extra heel expansion is a top cover material such as Spenco. So normally with, if you have PPT through the shell, we bevel out the inside of the heel cup, so it does not take up extra room within the heel cup, so we don't have to allow for extra heel expansion and bulk the device up. However, with Spenco, particularly 3 mil Spenco, we do have to add extra width to the heel cup in order to be able to accommodate it, because we can't bevel Spanko. Unfortunately, the material is as fantastic as the top cover material is. It's in this instance, it's a really negative one. So if you have somebody that's got a really wide heel and you know you're going to struggle with fitting that orthotic into a shoe and you want a traditional top heel cup, do not go for a Spanko top cover, because we can't thin it out. If you have a concave wedge, then it sits nicely on top of it and it does not take up any extra room. So that's extra heel expansion. So before I go into our medial flare and medial wrap, I might just ask if he's got any other questions there. Baz, do you have any questions?
Just a couple. The
Yeah.
first one is, in regards to cuboid notches, how is the sizing option of small, medium, large made? Is the actual size of the notch decided in relation to foot size, or is there specific measurements like 2, 4, and 6 mils?
Okay, so great question. So it is down to foot size. So a 4 mil medial heel scarf, for example, on a small foot will actually be quite large. A 4 mil medial heel scarf on a size 15 US male foot will actually be very small. The same goes for a cuboid notch. So a 4 mil cuboid notch on a little kid's foot will actually be quite large, and a 4 mil on a large foot will be quite small. So we've opted to go for small, medium, large, and from our experience over the years, we literally do it according to the foot size. So what we perceive to be, so a 4 mil might be the average, 3 mil cuboid notch might be the average for a size 9 US, and then we go from there. So great question. Anything else?
What top covers would you recommend for an EVA orthotic?
EVA orthotic? Okay, great, fantastic. Okay, so for an EVA orthotic, I would steer away from anything that will make the orthotic harder. Okay, for an EVA, you want softness. So Lunasoft, so leather, vinyl, PS Vlice, or PSV as we refer to it here at Footwork, all those materials do harden up. They don't have much stretch in them, and leather dries out and can change the shape of the orthotic itself. So I would steer away from those materials, particularly if you're having deeper heel cups and so forth. You want the material to reflect the top cover material to reflect and work with the shell material, being EVA. So look, Lunasoft is EVA, so that's probably one of the best ones. Spanko is a great material. It's soft. We can stretch it. We can actually fit nicely without having the device deform on us, which quite often can do. So Lunasoft, Spanko, and if you're looking for something really, really soft, Plastazote as a top cover for diabetics works really well. Now, Plastazote is something that you would use for somebody who's diabetic, doesn't walk around much, is not very active, because it is has very low resistance to shear stress. So that if they walk a lot, they'll destroy it. But that's not what it's used for. So anything that's soft, stretchy, and doesn't dry out is something that you want to utilize for EVA devices. Yep. Anything else?
Just one more. What is the height of the apex of cuboid notches?
We go again by millimeters. So it's around the sort of 2 to 3 millimeters in height, and then we stretch it out on a higher size. So, and then, but you can ask for it to be higher. Again, if you want to specify a given measurement, it's something we can work with, and it's very easy for us to give it to you. The same thing goes for arch heights, heel cup heights, medial flanges and so forth. Medial wraps or lateral flanges. Fantastic. So we'll move on to now a medial wrap and a medial flare. So a medial flare is a modifications where we literally, just like I did there, we widen the medial part of the shell, and we just modify it to give it a nicer finish. On average, it's about 4 to 5 mil wide. And again, in the top right-hand corner, I can actually see how much I've widened the midfoot by. So, and the function of the medial flare is to catch the navicular overhang, and the medial flare can increase the width, the height of the orthotic, because as we're pushing it out higher, it does go up at the height of the arch. Now, there are some podiatrists that like their medial flare to be flattened out because they find they get irritation, and the way we do that is we simply change that curve a little bit, and as you can see, we've now flattened out the top curve a little bit so it doesn't dig up so much. So if you want a flatter medial flare, we just ask for that in the comments. So a medial flare will catch that navicular overhand, give you a bit of width. Does it make a difference to the width of the shoe? We found not, simply because the shoes do open up as they go higher. So the upper of the shoe does open up a fair bit more. And what we found that we do a lot of orthotics for AFL players in New Zealand, the rugby players and so forth. And a lot of those athletes do require medial flares in their devices. Now, those devices are low profile and concave wedge to simply fit into the football boot, but they still do add medial flares because even a football boot will open up a little bit more as we move higher in the shoe, particularly in the arch. So a medial flare, you can ask for a small one. A small one will be 2 to 3 mil of width and does make a big change. The other thing that a medial flare will do, if you suspect the patient of having a medially displaced subtalar joint axis, we add more material medially to it, add more force medially to the subtalar joint axis, thus giving you more inversion. So whether, even if you've got a normal subtalar joint axis, by adding more force medially to it, we are creating a bigger lever arm, for a better word, thus creating more inversion moment. Bigger inversion moment is probably the right term to use. So that's a medial flare, as opposed to a medial wrap, which a medial wrap is probably better described as a high medial heel cup extending into the arch. Now, the average medial wrap is around 10 to 15 mil high, depending on the size of the foot. And a medial wrap will look something like that. A lot of times, we will need to add a medial flare to a medial wrap so that we do capture the width of the foot itself. So a medial wrap has to encompass the full width of the foot, because otherwise you'll get irritation. So if you've got a medial bulge in the scan, we will capture that with a medial wrap. So you don't necessarily have to ask for medial flare. If you notice that, we'll put that in automatically. So if I create my mesh now, there's my medial wrap. And as you can see, it's pressing all the way through on the medial side. So a medial wrap captures that medial side quite nicely. The time that you would use a medial wrap is probably tip post tendonitis or tip post dysfunction. A lot of podiatrists will use a medial wrap if a patient is not likely to be wearing a product such as a Ritchie brace or an Arizona brace, because they find it too bulky and so forth. So a medial wrap like that works quite well. With the 3D printing, that medial height there is 36 millimeters because it is a quite small foot. But, with 3D printing, we're not reliant on the size of the block. We can take that, as high as we want to be able to generate that shape. We can print that, so we can give you as much support as you require and create a bit of a different angle. So with 3D printing, the technology allows us to create those shapes, which we could never do in the past with machining. We could probably do it with vacuum pressing, but imagine doing something like that with vacuum pressing, how many folds you would actually get in the material, or how much you would have to overheat that material to get a finish like this. Carbon fiber, you could always use carbon fiber to do something like that. Unfortunately, you would need a massive piece of carbon fiber to be able to generate that. And the carbon fiber comes these days is pre-cut, the way that it's used in our industry. And a lot of those pre-cut materials aren't wide enough to be able to accommodate that. So again, 3D printing is something that this has allowed us to do. The other thing that it's also allowed us to do is provide you with a material or with a product that's cheaper. In this case, with a medial wrap, what we used to use is did a lot of work with Chris Bishop in Adelaide. What he was using for tip post dysfunction patient, a polypropylene device, and we would actually create the wrap, create a shape like that out of EVA, and it was called the Bishop wrap, and that worked fantastic. But it was very expensive to do, very labor intensive. We can get now the same effect with the 3D printing, because as we go higher, the material stretches out and becomes slightly thinner and becomes more flexible, so it's not as rigid as the whole device itself. And it's just one of the byproducts of our design software. We have some podiatrists that actually request for the medial wrap to be thinned out a little bit more. And again, just like we do with the sweet spots and so forth, we can just literally thin it out by a millimeter or so to give you that little bit more flexibility and take some of the rigidity away from the shell itself. So tip post dysfunction, a UCBL type device, etc., we can create it. So there's a medial wrap. Let me have a look what I've got next. This being a zero device, the heel seat is located in the center of the orthotic, okay? We now can add an aperture to it. So there's my aperture, and I can increase the size. So there's my, move it around a little bit more. So that would be, again, small, medium, large. And the size of the aperture is relative not just to the size of the orthotic, but also to the size of the heel seat. So if I wanted to do a large one, let's start off with a large one. I'll make it the full width. So that would be my large heel aperture. And I create that. And there's my large heel aperture. If I wanted that to be on the smaller side, so that would be my medium, and a small one would be like that as well. Now, we do get requests every now and then from podiatrists to put an aperture where mid-cal tubercle enthesopathy would be. So we would move it around to that region. The problem with that, if we stick it there, is that we've now got all this thickness through the shell. And we've weakened the shell itself. So in that case, the better option would be a sweet spot, which is something we're going to cover very shortly. So the heel aperture that we do here at Footwork is located at the lowest part of the heel seat. It is simply there to drop the orthotic lower inside a shoe. Some podiatrists do use it in order to be able to generate some more cushioning feel in the orthotic by putting a paw and button in there. But the more laterally we go, so if I was to now go into posterior view, now if I was to invert that, let's say simply by 5 degrees, bring that up to the floor. So you can see that reef would be at a 4-degree angle, create a mesh. Now you'll notice the heel seat is more laterally. So therefore the lowest part of the heel seat is around this region. It's set off more laterally. So therefore the aperture will be located more laterally. Again, the function of the heel aperture on a prescription form is to drop the orthotic lower inside the shoe. It's not to offload, particularly in a 3D printed device. So much so that we only put apertures in devices of single degree correction. Anything of 10 degrees or higher, we don't put, because the heel seat is so lateral and so small, it just defeats the purpose of an aperture. And then more so with a concave wedge, where you don't have any meat or any shell thickness on the lateral side with 10 degrees or higher inversion, we can't put the aperture in there. So that's the function of a heel aperture. Any questions, Baz?
We have one question. What would be the best cover for medial wrap? Could you use Spenco?
Spenco is perfect. Something that we can stretch, because there's a lot of stretching that needs to be done in order to accommodate it and squeeze the top cover in. So Spenco top cover is perfect. It's our recommended top cover for medial wraps. Lunasoft as well. It works very well. Again, I'd steer away from anything that does not stretch, such as leather or vinyl or PS Glice. So Spenco and Lunasoft work really well, but probably Spenco is the best one. With a lot of that medial wrapping around, you can get a little bit of shear and a bit of rubbing on the foot, and Spenco is much smoother, whereas the Lunasoft top cover, EVA based, can grip a little bit more and can maybe irritate, or actually the cover can wear away a little bit quicker. So Spenco top cover by all means.
Yeah, that's all.
That's it. Okay, fantastic. So the next one on our list was a gate plate. Now, a gate plate, the way that we do it here at Footwork, we do it purely for in-toeing, where we literally take extend the lateral part of the orthotic just beyond the little toe, or the fifth toe, and we just balance it out so it goes all the way to there. I'm not going to go into why would you use a gate plate or why you wouldn't and so forth. That's probably a discussion for another day. So there's my gate plate extension. Okay, so why would I use a gate plate? Why wouldn't? It's purely used for in-toeing. We had the odd request maybe once or twice a year for a medial gate plate for out-toeing. We don't do that here at Footwork. We do not do, simply as a matter of principle, because medial gate plate jams up the first tray, and for a kid that is a big no-no. That's probably the only thing that I'll say at this stage. And a medial gate plate is a Morton's extension, which is something that we do. Again, here at Footwork. So if I go File, Open Up, if I go into a Morton's extension, a gate plate is something that we'll probably cover in a totally separate a video workshop type thing. So a Morton's extension, again, with our medial extension, is something that we do here, and our standard Morton extension extends to the end of the first or the hallux. We make it slightly wider to encompass the width of the toe itself. There is our Morton's extension. So since what we found, since we've been 3D printing, our Morton's extensions have become far more popular, so much so that we'll do on average probably 2 or 3 a day, whereas we used to do those 2 or 3 a week. So match the thickness of the Morton's extension the same as the shell. You can request it to be thicker or thinner if you want to, and we do taper it off slightly towards the end of the toe. So that is a standard length which goes to the end of the first toe or the hallux. A short Morton's extension will go to will just cover the MTPJ joint. So go into literally the web space. So my short Morton's extension in this case would look something like this. So there's my short Morton's extension, okay? And a long Morton extension will extend it another 5 to 10 mil depending on the length of the foot past the big toe itself. So a Morton's extension, why would you use it? If you need to splint the first MTPJ because its patient has got a severe hallux limitus or a hallux rigitus. A Morton's extension will not promote first ray functions, as some people tend to think. A Morton's extension is purely there to splint it and reduce first ray function. So something that you perhaps do not want to combine with a Morton's extension is 4-foot valgus wedging or 4-foot valgus padding, because it literally works against it, okay? So it's something that, like I said, it's become really popular in the right cases, in the right instance. We've fitted Morton's extension into AFL players' football boots and so forth. So they do work really well. We now have the ability to actually do a Morton's extension, just like we did with the EVA. So do a full-length full-length 3D printed device. And what we would normally do, let's say 3 mil device with a 1.5 mil full extension and then a Morton's extension built into it. So we can modify that as well. If you wanted to do that, so if I go into, let's say I'd go into my EVA device, which gives me my full length extension straight off. So if I generate this, so there's my full length printed device. And the only difference between printing and EVA is when we select the output file, whether it goes to a CNC machine for EVA or whether it goes to the 3D printer for 3D printing, but we use exactly the same design. So in this case, we've got a 2.5 mil shell with a 1 millimeter forefoot. So let's create that. So as you can see here, we have a 2.5 mil shell, 1.5 mil forefoot, slightly thinner. And now if I was to just remove the transparency, and now if I want to stiffen up the first ray, we simply use our little magic tool, and we literally, for demonstration purposes, and we've literally stiffened up the medial part under the first MTPJ, just created a Morton's extension inbuilt into the shell. Now that's quite a large one. I did that on purpose so you can actually see the difference between the materials, and we can do that quite easily, 3D print that and having the full length of the device. One tip, why would you use it? Some podiatrists use it because they don't want to see that transition between the Morton's extension, the rest of the shell, and the 1.5 mil shell in the forefoot does create a little bit more flexibility and so forth. That's one reason. One case study that we had with a podiatrist was one of the sports podiatrists in the AFL system, where he found that that fitted perfectly into the player's football boots. Now, we were supplied with a template, like I showed you previously, where we had a template of the actual insole of the shoe, because if we're going to print it, we want to print it perfectly. So make sure if you're going to do that, you supply us with the insole template. And again, the way you do a template, simply take a photo of it, supply us with the length from the end of the device to the heel, and then we can match it up to the size and expand it if we need to. If it's shrunk, we take care of it here. But that would be a full-length 3D printed device with an inbuilt mortise extension. That device has got a nickname. It's called the Tommy, named after the podiatrist that actually did it. So there's a mortise extension. Next thing on my list is shell shape and shell length and sweet spots, and that's pretty much it. Our standard shell, we determine the width of the heel by adding 4 mil heel expansion to your scan already or to your cast, and then we go slightly medial of the bisection of the first MTPJ, just inside the 5th MTPJ, the full width of the 5th MTPJ, making the forefoot slightly wider than the rear foot and giving you a nice anatomical shape. With a low profile device, what we give you, so in here in the rear foot width is 58 millimeters. We give you 1 millimeter less heel expansion, and we narrow the orthotic and make it fairly straight. So fairly straight is probably the operative word. We don't want to make it too straight because sometimes it does look a lot more like a pedal pop stick. So what visually can look straight, when we actually take the measurements, it does not appear to be so. So again, don't want to spend too much time on it, but as you can see, now we've got a much lower bulk device. So we've got a narrower heel cup by 1 millimeter. We've narrowed the forefoot significantly. But if I look at the measurements itself, so diameter is 57, the forefoot width is 63. So it's still 5 mil wider than the rear foot. If I was to bring it in to 57 in the forefoot, it will actually look much narrower. So we do cut it from appearance shape, what looks like to be fairly straight, just tidy that up a little bit. So there's my low profile. The other option is full width or wide shell. And wide shell, we go back to 4 mil heel expansion, and we literally give you the full width of the orthotic itself. So we just grab that. In this case, it would look something like this. And again, that's just a quick representation. We do it for a best fit. That patient's got a bit of a HAV or enlarged first MTPJ, which we probably accommodate for. And that would be my wide fitting orthotic shell. That's still got a remnants of a bit of a medial flare on it. So we tidy that up obviously as well, but you get the gist of the exercise. So that's our full width. Orthotic length is the next thing that we'll do. If we look at length, the way we design devices here at Footwork, we go first MTPJ, just below the first MTPJ, just below the 5th MTPJ, and obviously we go to the back. Some podiatrists would want the device to be made longer, and we literally expanded. For consistency, we actually lengthen the device from the rear foot. So we'd literally, if you want it longer, we make it longer by 12 millimeters. So the length of the device is 149. We'd make that 154. Okay. So there's my longer device. Why would you want a longer device? There are 2 reasons podiatrists will ask for a longer device. Number one, I don't agree with, is something that they would use with their child because they want the child to have the device for a longer period of time. They want some growth in the device. So for the period that device is on the longer side, if I stretch that back, we are jamming up first ray function and obviously impinging MTPJs and so forth. So it's something that I would not agree with a custom-made device. The other reason why you'd want a longer device, we take non-weight bearing scans. Most podiatrists take non-weight bearing scans. And for that purpose, if you do know that weight bearing, the scan will, the foot will elongate upon weight bearing, you may want to choose a longer option because it gives you a much better representation. There are podiatrists that take semi-weight bearing scans that has other connotations and implications, such as arch heights and so forth, and it's something we'll probably cover in another tutorial. So there's length and short. We again shorten it the same amount, but we bring it in by 5 millimeters. Why would you choose a short one? Simply because there's 1 or 2 podiatrists that think that our orthotics are too long as a standard to the way they like them to be done. They like the device is slightly shorter. Fantastic, we can do it. And it's another representation that we can do whatever you want as long as you know how to ask for it. So if you're not sure how to ask for the things, we can design those things in front of you, whether that's using networks such as Zoom or TeamViewer, or you come and spend some time with us here at Footwork, and show us how you want your devices made. We'll show you how to ask for the things that you want. One last thing is a sweet spot. So a sweet spot, we kind of showed you already with the EVAs when we showed the offloading, but a sweet spot, most common one that we do is in the mid-cal tubercle area. Again, that's a little bit big because it's a smaller orthotic. So we'd place it literally at the base of the heel on the medial side, and where the plantar fascial accommodation would start. And if I create that, there's my sweet spot. You can see there's a indentation in the orthotic itself. Now, you can have a sweet spot. You can place a sweet spot anywhere on the shell. So if you've got a subluxed medial cuneiform, we can place a sweet spot there. So if I wanted to add another one, sweet spot, let's say, grab that, we place it in here and create it, medial cuneiform, we can do it there. We tidy it up a little bit more. We can also have custom sweet spots. So if I wanted to have a custom one and offload different things, we can do that too. And the best way to mark a sweet spot for us is for you to place a felt dot on the foot prior to scanning, and therefore we'll have that indentation and see exactly where it is. Photos and diagrams help, but if I have that indentation of the that on the scan itself, I know exactly where to place that sweet spot. So that's the last of the modifications. Last thing we've got left over is our heel stabilizers. It's probably something that we'll cover in our next one when we go into covers and so forth. So, Baz, do we have any questions?
Yeah, we have two more. One of them is for peds, what would you recommend patients who are out-towing if you don't recommend medial gate plates?
Okay, out-towing. Look, for an out-towing patient, are you trying to control the out-towing? If you're trying to control or make an in-tow, you've got to find out, one, what's causing it, okay? So if it's coming from the hips, stretching and strengthening. It's the only way you're going to be able to do it. If it's internal torsion, again, there's not much you can do. If the patient's out-towing, they are going to collapse their arch a little bit more. So you've got to make sure that you're probably looking at more frontal plane correction from the device itself. So you wouldn't make the device too archy, but concentrate more on the rear foot. So whether they have a higher calc inclination angle, would be using a CB modification or a triplanar heel skive. Or if the patient's got a low calc inclination angle or a flat foot, you'd be using more of an inverted device. But from our experience over 25 years, there's probably not much that you would do from an orthotic specifically to make a patient in-tow.
Next question is the mortise extension durable with the nylon material used in 3D printing, or can it snap like polypropylene?
It can snap. Any material can snap. Carbon fiber snaps. But what we found is that it snaps much less than what the polypropylene did. Like we would probably have, like I said, we would make 2 to 3 of those a day over the past year. And we've probably replaced 4 or 5 from memory. Someone may correct me if I'm wrong, but from memory, we would have replaced 4 or 5. That'd be 1 or 2 more plus or minus. But it's far more durable. And if it does snap, we'll replace it for you.
Final question is, what is the best way to mark out sweet spots on plaster casts?
On a plaster cast, just draw it. If the sweet spot is not there, like if the cast does not capture the sweet spot, just draw it on a plaster cast, and we'll take care of it in here. We can then add things to it or push it out when we have it here. If you want to push it out while the plaster is still somewhat wet, not fully dry, when you've pulled it off and you can push it out, great, but just draw it on the plaster cast is sufficient now.
Great. Yep, that's all.
That's it. So if you have no more questions, we'll finish up on that and hope you can catch us next time.
Thanks, Art.
Thank you, Baz.